In this video, we're going to do a quick overview of atomic structure. Hopefully this is review. If it's not, and you need a little bit more background, you might want to do some reading. Recall that atoms are made up of a nucleus, shown here, which consists of both protons and neutrons. Atoms also have an electron cloud, which is where the electrons hang out. And don't forget that you have the same number of protons as electrons. Now, where electrons hang out are in these orbitals. And you can see two examples of orbitals here. The s orbital is spherical. And what you're looking at here with the s orbital is the probability we're finding that electron is highest. So it has a very good chance of being in this orbital. With the p orbital, you can see that the shape is a little bit different. It looks more like a figure 8. And again, what we're seeing with the p orbital is a high probability of finding the electron or electrons in that orbital. So for the s orbital, that means that you have the highest probability of finding that electron in that spherical shape. With the p orbital, things are kind of weird because you have a high probability of finding the electron here, but at that same distance, the probability of finding that electron is extremely low. And so we don't expect to see the electron here. There are more orbitals, but for the purposes of organic chemistry, we're primarily going to look at the s orbital and the p orbital. We're also going to see in the future that these orbitals can combine and hybridize in some instances. As we look at the periodic table, you'll see that we have different atomic orbitals. So here's the 1s orbital shown here. And as we go down the periodic table, or up in energy, then we'll get to the 2s orbital. And then we'll hit the 3s orbital. And you'll notice that these are getting bigger in terms of size, and they're also increasing in terms of energy. So each of these orbitals is associated with a shell based on their principal quantum number, n. For the 1s orbital, that means n is 1. And for the 2s orbital, n equals 2, and so on. And as I mentioned, with increasing shell numbers, so as we go from 1 to 2 and from 2 to 3, we're increasing in terms of size and energy. One of the things that we really need to be able to do is to find the valence for an atom. And to do that, it's going to be helpful if you remember how to obtain an atom's ground state electron configuration. So we're going to review the rules for doing that. Pauli's exclusion principle says that no more than 2 electrons can occupy a single orbital. That means that once we add 2 electrons to an orbital, we can't add any more. We also know from Pauli's exclusion principle that if we have 2 electrons in the same orbital, they have to have opposite spins. And those are represented spin up and spin down. The Aufbau principle tells us that each electron must fill the lowest energy orbital available. So we're going to fill from the bottom up. And Hund's rule tells us that all orbitals at the same energy must contain a single electron before we can add that second electron that's the opposite spin. We're going to quickly go through how to work this out for carbon. So here's our periodic table. Carbon is right here, and you'll see that it has an atomic number of 6. So if we have 6 electrons, that means we're first going to fill the 1s orbital with 2 electrons, one up and one down. Then the next orbital would be the 2s, which we would also fill with 2 electrons. And then we have the 2p. There are 3 types of p orbitals: the px, the py, and the pz. If you remember what our p orbital looks like, it looks kind of like a figure 8. So this would be the py in the y-axis. Then we have the px in the x-axis, and the pz. So that's what those 3 orbitals are: the px, the py, and the pz. Well, we've already used 4 electrons, so we only have 2 left. We're going to put 1 here and then 1 there. So we've obeyed Pauli's exclusion principle because we only have 2 electrons in each of these orbitals here. We don't have 3 or something like that. We also made sure that we put 1 spin up and spin down. Let's look at this in terms of energy so we can see how we applied the Aufbau principle and Hund's rule. So the Aufbau principle told us that we had to fill these in terms of energy level. And you'll see that we did that. We filled 1s first, then we filled 2s, which was the next lowest in energy, and then we started filling 2p. And it's kind of a little bit hard to tell here, but 2p is just a hair higher in energy than 2s. So that was the Aufbau principle. And then Hund's rule told us that when we have equal energy level orbitals, that we can't pair them up until they're all filled. And so that's what we did, is we put one here and then one here. We can't start pairing these up until we fill up this one, and then we can start filling them in. So that's how we do ground state electron configuration for carbon. What we really want to be able to do with this information is to determine valence. And valence electrons are the electrons that occupy the highest energy shell. For carbon, we're looking at this shell here, our N equals 2 shell. And we have 4 electrons in this shell, so valence for carbon is equal to 4. If we were doing the same thing for hydrogen, hydrogen only has 1 electron in the 1s orbital, so valence for hydrogen is 1. I recommend that you practice with valence and make sure that you can quickly determine valence for anything in the first 2 rows of the periodic table here.